Hi, welcome to another video, and this time it is about the large language model. If you're attempting to study large language model, the transformer architecture, etc., this high-level video is going to give you the clarity that you need to understand what we are trying to do. So this is my attempt to bring that clarity. In addition to this video, I will also give you a playground utility which I have created for you to experiment with. Okay, so this will give you a very nice understanding and introduction to the large language model. Welcome to Techie Talks AI. I'm Sri from Shogini. On this channel, we bring you hands-on demonstrations and insights into the latest tools and trends to help you get started with ease. Don't forget to subscribe and be a part of our journey into the future of technology. So this is not the complete transformer architecture. We are just focusing on the decoder part implemented in GPTs. Let's begin. So here we have an image of a three-dimensional object, a sphere containing number of tokens. So imagine this to be a sphere that has all the English language vocabulary. But when I say all, consider it as limited to 50257 tokens. So for all practical purposes, consider a token as one unit, like one word or one alphabet, or it can even be a partial word. Now this could have been an alphabet, this could have been a complete word, but a balance between a complete word and a single character offers the best performance. So we don't need to get into details. Understand that there is a multi-dimensional sphere containing all English language tokens. We will focus only on one language, English language tokens. Any input sentence this large language model can handle will have to be present in this object. Clear? Now I say this is a three-dimensional ball. This is not three-dimensional ball. This will have much higher dimensions. Like transformer architecture had 512, GPT-2 has 768, and other models have 1536 and more. So can you imagine an object with these many dimensions? Absolutely not, right? So you take a single word here, a token, say parrot or rabbit. Okay, now normally in 3D space, the rabbit will have X, Y, Z coordinates, right? But in this case, or in this case, or in this case, it will have these many number of coordinates. Clear? Each coordinate can be seen as some feature. Maybe one coordinate is it a mammal? Can it jump? All these features can form these coordinates, but they are not strictly feature-wise grouped. It is learned using an automated way. So this classification will not make any sense to we humans, but know that every token has these many dimensions or these many coordinates in this hyperspace. So just to summarize, we have a very sophisticated object that has all the possible English language alphabets to words to tokens, or all possible subwords. Don't worry too much about the characters, etc. Something like a dictionary, but in our case it only has 50,257 tokens. Tokens are group of alphabets like words or subwords. Each of those will have, let's take the case of GPT-2, 768 numbers attached to it. So each of those tokens will have 768 individual numbers attached to it. And these numbers will have some meaning to the property. So in this object, similar tokens can get grouped. For instance, things that can fly in certain dimensions will come close. Things that can jump like frog, rabbits, may in certain features may get grouped in some location. So such an object is beyond our imagination, but know that this object has all the words, and each of those words have a vector attached, and that vector is 768 long. Do you understand this well? So each token has 768 numbers attached to it, and these numbers are not simply assigned to it. During training, they found similarity, and those numbers have certain similarities, so that in this hyperspace, these tokens with similar meanings will come closer. Okay, so if this is fish and if this is water, they may be close. And if this is a bird and this is sky, this may be close in certain dimensions. So understand that if you have a sentence like this put into our LLM, maybe this is pointing to parrot and this token is pointing to can, and then the large language model has to predict the next token. In the start, this embedding or the vector for this can could be here. Whole aim is to push this can to some contextually relevant location where our needed word is present, like fly. Then it generates the word parrots can fly. So our aim is to get the final word pushed closer to the next word. That is our aim. Okay, so let's see how it happens. So I have the picture here. Okay, so here, this is our world. So this large language model will only accept words which are present here, and it will only generate words which are present here. And these are not complete words. They are called tokens. Consider it as subwords, partial words. So this part is clear. First thing, we have a sentence coming in. I love parrots, especially their vibrant. That is the sentence that is going to enter the large language model. So we are going to understand quickly what happens. Okay, so this is the input. The sentence enters the large language model. Next thing that happens is the sentence gets split into tokens or subwords. So what we will do is, we will complete the flow, then we will go through the playground. The sentence gets split into subwords, then those subwords will be looked up to get an ID corresponding to each of those subwords. That is, every token that is present here has a number. Let me repeat, every token present here has a unique number. Remember, these numbers are not the vectors. These are meaningless numbers, but every token has a corresponding unique number. This sentence reaches here, it gets tokenized. From here onwards, this sentence is ignored and we only carry forward the token IDs. Next thing is, every token ID has a corresponding embedding. Like I said, a vector of 768 dimensions or even much more. So every token now gets a sequence of coordinates which are 768 long. That means you have made the token much more meaningful. That is, like I said, token ID has no meaning. Now we have added meaning to our token IDs. So semantically meaningful numbers we have attached to our token IDs. That means similarly meaning tokens will have similar group of numbers, or they are closer in this hyperdimensional space. We will actually see this happening. Moving forward, we ignore the token IDs as well. That is, input sequence be converted into subword, and then we converted that to token IDs, we don't need the input sequence and the subwords moving forward. We only needed the token ID. But after this stage, we don't even need the token IDs. So now we have embedding for each of our tokens. Embedding is a vector with 768 coordinates attached to it. Then a very interesting thing happens. That is, you add another number to this. So like I said, here we have added the semantic data, semantic information. That is, the tokens at this stage will have meaning. Each word will have a meaning attached to it. Here we are indicating the position of those tokens. We will not go into the technicalities of it, but what we are doing is we are going to add a sine wave to this semantic information, but a single sine wave cannot indicate the direction, position of the token, whether it is first, second, third, or whatever. So in this sequence, see, this is the first word, second word, third word, fourth, fifth, sixth. So if you attach a sine wave to the token, we cannot indicate whether it is on the left side or on the right side of the current word. For that, you need a phase difference. For that, you need a cos wave also. So when you have sine and cos attached, at any given point, we will know which quadrant that specific token is. It will have a direction. Cleverly, with the sine and cos wave addition to this token sequence, we can indicate to the embedding that there is an order in the sequence of tokens. So let me erase this. Here we are adding positional information that will indicate the sequence. Here we have added the meaning of individual tokens, and here we have added the sequence of the tokens appearing in the input. So we can easily understand that meaning of individual tokens is important for us to predict the next token. But we also need to know the position of the word for us to correctly capture the context. So do you agree that the embedding after adding the positional information has become much more richer in its meaning? So now what happens? After this, a fairly complex sequence of operations which we will address in detail in the next video. But know that here we are going to add contextual meaning to our tokens. What is this? We have got semantic meaning, we have got positional information added to it, but that is not enough. We need to know the influence of all the words to the current word. Okay. Then only we will be able to predict the next word. So if this is the current word there, we should know how much other words are pertinent for this word there. Okay, so that is called contextual information. That is added here. Okay, so at this stage we only need to know that semantically meaningful embedding vector is not enough. We also needed to encode the position so that order of the token will also have an influence in the next word prediction. But here we are saying even that is not enough. We also need to know significance of all other words appearing before to correctly know the context. We will go in depth in this block in the next video. Once we have the contextualized vector obtained, we can ignore all these things. We only need the contextualized vectors and then go further at this stage. See, let's take the case of this word vibrant that has been tokenized here. Then we got the embedding for that word vibrant, and imagine that this was the location the word vibrant existed at this location. But after contextualizing the embedding, this vibrant may have moved closer to colors. Imagine that this is the location where the embedding colors existed, and the contextual vector may have moved the word vibrant. So this was vibrant at start. This is where vibrant moved after contextualizing, after going through this operation. And then here in softmax, it takes the probability of all the words that are nearby in this vocab, will pick the most probable word, and it predicts colors. So this is a high level understanding of what this LLM is attempting to do. Clear? So it revolves around this vocab, which very often is not emphasized in most of the videos. Input is this vocab, output also is picked up from this vocab, which is made up of vectors or embedding. Whole aim is to shift this last word closer to our target word so that we are able to predict the next word. Clear? So now what we are going to do is, we are going to see this practically. The URL of this playground application is given in the description. So this is the playground that I have created to learn up to the attention. That is, just before the attention heads has been made very clear and you can play with it. So here I have a word, I have a sequence, hello world. I have selected embedding dimensions of 3. So this 3 for GPT-2, this is 768, and for other bigger models it can be double or even more than this. What it means, that many unique numbers will form the meaning of this embeddings. And then first thing that happens is subword splitting. Let's click on this generate. So what is happening here is hello has been converted to one word token with this ID, token ID 15496. World without the exclamation mark has been converted to ID 995. Then the exclamation mark is treated as another token with ID 0. Clear? And the tokenizer that we are using is a tick token. So this tick tokenizer.versal.app is a popular tokenizer for us to explore. If you select GPT-2 and enter hello world exclamation, you will notice that 154962519. Okay, our world is small letters, so let's make this small letters. So see here, 995, 15496, 995 and 0. Those are our tokens and token ID. So these are the tokens and these are token ID. So in this playground, this input sentence sequence has been converted into subwords, and then each of those subwords have a token ID. So far is clear? Know that this token ID has no meaning. There are some arbitrarily picked number its magnitude has no significance, but there is a unique number for every token. So always hello with uppercase H has this token ID 15496 for this tick token, which is GPT-2 tokenizer. Okay, so this part is clear. So we have converted our input sequence to token IDs. Next is, if you click on any one token here, you will notice that our embedding dimension of 3 will have 3 coordinates to represent its meaning. So here dimension 1 is minus 0.77, dimension 2 is minus 0.83, and dimension 3 is minus 0.80. So what are these? So these are the coordinates of the vector in a 3-dimensional space. But in reality, as mentioned before, this is a 768-dimensional vector. That will be very big. Let me increase this. I will make it, say, 20. Okay, and if I generate the embedding, you will notice that hello now has 20 dimensions to represent its meaning. So this embedding is clear. Embedding is a vector to give our word or tokens semantically meaningful set of coordinates. So in reality for GPT-2 it will be 768 numbers. So that is the embedding dimension. So if you enter 768, it will be very big. See, we get a warning. But if you click on hello, okay, you will notice that we have 768 numbers to give the word hello its meaning, semantic identity. Okay, so this is, I don't think there is anywhere else you can find something where you can go up to any dimension that you want. So let's put it back to 3 to make it manageable. So hello has 3, let's close it. World has 3 embedding coordinates, and exclamation mark token also has 3 coordinates. Those are the embeddings. So far is clear. Now what do we need to do? We need to add a mechanism called sinusoidal encoding to indicate the position that hello comes first, world is the second in order, and exclamation is the third in the sequence. So that is what, if you click here, position encoding sine cos. So here it starts like this: sine 0, value 0, cos 0, value 1. It goes on like this. So that is the positional encoding. So let me make this bigger. Okay, I made dimension 6. Now if you see the positional encoding, you will notice that the hello being the first word, the positional encoding switches between 0 and 1, 0 and 1. Okay, because this is the first word. So the position and information is going to be 0, 1, 0, 1, 0, 1, like that in this coordinate. Hello being the first word, the position information that we got is 0, 1, 0, 1, 0, 1. And then what happens is we add our original embedding and the positional information. This is where the result is. So first coordinate is minus 0.99. We have to add 0 with it. So we got minus 0.99, same value. Next value in the embedding is 0.15. And that we will add with 1 to get 1.15. So is this clear how positional information is getting added to our embedding? So this final value is going to be carried forward. So if you look here, we are at this location, adding positional encoding to our input embedding. Same thing happens for every token. So next word, the word is the second token in the sequence, right? So here, this is the input embedding, and positional encoding is 0.84 for the sine, and for cos it is 0.54. So the waveform is slowly shifting in one direction, and adding both, that is 0.84 and this 0.09, we'll get the first dimension here. See, 0.84 plus 0.09, you get 0.93. So it goes on like this. So let's close these. And then finally, here I'm showing the outputs. So first token ID will have, for our six dimensions, we'll have these coordinates, 0.9894. How is this number arrived? This is adding the dimension 1 of embedding of the first token plus the positional value of the dimension 1 of the first token. So let's see the number, 0.9894. If you round it off to 2 digits, it will be 0.99, right? So let's look at this hello. See here, 0.99 plus this 0. So it will be minus. So this is minus 0.99. Next one is, dimension 2 is 1.1496. So it will be rounded off to 1.15. In this slider, we have the rounded off value. So here, this is 0.15 plus 1. So you get 1.15. So it goes on like this. So once you have this part clear, you can play with it. These are all calculated, computed live. Once this part is clear, journey into the attention head will become much more clearer for us to follow. Okay, so next video we'll tackle attention head. So coming back to our diagram, this is the input sequence which we enter. Here we have the same input sequence received at the input of our LLM. It is split into subword tokens. Then each of those subwords will have a unique token ID which are meaningless, and those token IDs get meaning by adding a vector to each of those tokens. GPT-2 has 768 dimensional vector. And then next is, we attach the positional encoding here, and we saw the calculation, how this addition happens. We reached up till here, and now we need to study this in the next video, where we will give contextual information. At this stage, our hello, world, etc., and the exclamation, etc., could be in different locations in our sequence. Once we add the contextual information, so here we will add contextual sense to our embedding. Okay, so we will see how that is done in the next video. Okay, so if you have any questions, please come by the comment section. Thank you for your time. Please remember to like, share and subscribe. See you in the next video. Bye-bye.